The times they are changing, and speaking of time, it's 4:15, so let's move on to the next portion of our presentation. Murphy Brothers Contracting welcomes the rest of our audience of building design professionals interested in quality continuing education. Today's credited presentation, thermally broken shelf angle design for masonry and stone facades. Ron, you look good. You looked a little jet lagged. Just got back from Iceland, the land of geothermal.
Yeah, it was great actually. 100% renewable electricity there from geothermal and hydroelectricity. It was amazing. Waterfalls, glaciers, lava caves. It was incredible. Just a wonderful vacation. And yeah, I'm a little jet lagged, but not too bad.
Sounds like a presentation in of itself. And so hold on to your seats. This is another HSW AIA approved credited session. I'm your host, Michael Murphy, on behalf of Murphy Brothers Contracting. I'd like to thank you all for joining us. Today's presentation coming to you live on the ubiquitous Earthkind Energy Zoom platform. Murphy Brothers Contracting is known throughout the greater Westchester, Hudson Valley, and Southern Fairfield region for award-winning residential and light commercial construction projects. The Murphy Brothers team would love to work with you. Visit our website at murphybrothers.com or call us at 914-777-5777. A big thanks to our sponsors today, Earthkind Energy. Ron, take it away.
Well, thank you very much, Michael. Really appreciate it. It's always a pleasure being part of this outstanding series of presentations that Murphy Brothers has been putting on for 15 years now. How long has it been, Michael?
Seems like yesterday.
I know, it's just incredible, and hopefully we'll get back to being in person sometime soon. But real quickly, Earthkind Energy Consulting represents property owners who want to make these transitions, specifically focused on the clean energy aspects of technologies and energy and financing. And just to give you a sense on the economics of the stuff, it's pretty incredible right now, especially in Westchester, where you could take a project, a relatively small project. This is one that the owner was looking at a $200,000 gross investment, but they were getting half of that back from a cash incentive from New York State. That meant that almost half of it basically was being paid for in a cash grant right to the bottom line. They then looked at their tax credits and bonus depreciation and found that that took them down to only $10,000 net investment. And then because this was a new construction project, or if it's a roof replacement, you can actually build some of that cost into the credits as well. And what happens is that they wound up with a net cost and actually a net positive impact to their bottom line. And then they started saving $13,000 a year in electricity savings just by going solar now today with modern technology. Similarly, when we take a look at heat pumps now, both air and ground source heat pumps, and you take a look at oil or propane or natural gas, and you take a look at both the monthly and the annual operating costs, you find that these air source heat pumps, which are really just air conditioners that also grab heat out of the air, even down to minus 15 now, can reduce your energy costs by over 50%. And then the best technology is really for heating and cooling is geothermal. You use that heat beneath our feet, as is done in Iceland in many amazing ways, but we can do it right here too, because when you go down below 5 feet in this part of the world, you get a constant 50 degrees temperature, and that means that starting temperatures for geothermal are fantastic. 50 degrees, you can almost cool your building with that just without any additional energy, and that's similarly just a little bit of bump and you wind up heating as well and getting your hot water. So tremendous savings opportunities with clean energy technologies. We can talk about them in length, but the fascinating thing is don't leave money on the table. There's opportunities out there. There's a lot of incentives out there. Maximize your return on investment and give us a call. That's what we're here for. Earthkind Energy Consultant would love to work with you anytime, any place. Michael, back to you.
Right on, Ron. Well, you did mention going live, and yes, we are going to go live, absolutely live on Thursday, October 13th at Westchester Magazine's headquarters in Rye with Michelle Schutt-Ing. Some of you know her from Certainteed. She's going to be doing a presentation live at Westchester Magazine for us. Look for the invitation. You know, there'll be food and adult beverages and a great live presentations. So that'll happen in October 13th. If you'd like AIA credit for this session and you haven't already, please send me your 8-digit AIA number. All in attendance will receive by email an official attendance certificate courtesy of all the good folks at Faro. During the presentation, Mr. Earthkind himself, Ron Kamen, will be collecting your questions for our presenter in our official Zoom chat box And we'll tackle these questions with today's speaker following his presentation, which means you're all on mute, so sit back and enjoy. This AIA-accredited portion of our presentation, thermally broken shelf angle design for masonry and stone facades. Our presenter today is the sales director for Faro, overseeing the sales and marketing for all Faro products throughout North America. He brings more than 20 years of senior experience in innovative construction products, particularly focused on concrete, masonry, and thermal performance, providing a technical, collaborative, and relationship-based approach to Faro's business. Coming to you live from, Adam, where are you today?
I live in New Orleans.
He's in New Orleans.
Yeah.
Here's Adam Kimball. Take it away, Adam.
Hi, everybody. I'll just go ahead and get this shared, our presentation. So just bear with me as we get this pulled up. Okay, just somebody give me a confirmation that we're on the right screen today.
You are there.
Great. Okay, bear with me. There, perfect. Hi, everybody. Thank you for joining us today to learn about our energy efficient wall assemblies, considerations in masonry buildings presentation. My name is Adam Kimball. I am a structural engineer by training. A little bit about Faro as we get started. This is AIA credit presentation, like Michael mentioned. So if you haven't given them your credit number, please do so. We can also provide certificates if you're looking for continuing education credits that you could self-report at other locations. But a little bit about Faro. So it was founded in 1995 by a group of structural engineers. Faro is located in Edmonton, Alberta, Canada. So if we're talking about energy efficiency and thermal performance, Canada has generally been more progressive in this. So we think about insulation thicknesses in North America as a thick wall, or a thick insulative wall, 3 to 4 inches. It's pretty common in Canada to have up to 6 or 8 inches of insulation outbound of your structure. So being that the case, you'll see this in our presentation as the insulations got thicker, the wall assemblies, especially with masonry, were becoming more difficult design, and hence the creation of Faro. And the things that we focus on are the engineering side of masonry accessories. We do sell the common masonry ties and things like that, but what we really focus on are the things that you see here. And these are generally going to be supported by our 5 structural engineers that are on staff and the other CAD drafters. And so those things are our Faro fast thermal bracket, offset shelf angle system, which we'll be speaking about today, our thermal masonry ties, our Faro breakaway fire release connectors, and other custom structural connections. So not only do we offer masonry connections, but it could be other stone connections, both cultured or quarried, or other facades such as metal panels or fiber cement boards, EIFS, etc. So the thing that we'll be talking about today is the current challenge designing efficient masonry wall systems to meet the demands of expanding energy codes and guidelines. So you're starting to see this trend happening more. Again, it happened 5 to 7 years ago in Canada, where the energy codes were starting to regulate specific thermal bridging locations in a building. We're starting to see that happening more often, especially in the big cities. So you see that last May in 2021, I believe, all the years of COVID has made me forget about what year it is. And so the new code requirement requires you to calculate the energy loss at specific locations that thermal bridging would happen, which would be commonly, for instance, in balconies, parapet wall conditions, and masonry conditions. And so that's what we really focus on. And so this is what you would commonly see as a problem. So this is effectively a non-performing code. This is non-code compliant, for instance, in New York City. And the reason why that is the case is that, as I can show you, we have our insulation here. And so this is a great start, but with masonry walls, which everybody would generally want, this is a more aesthetically pleasing wall, and in addition to that, it's a more durable wall. But the problem that we have here is that we have this angle, and so the more insulation we have, the further brick comes out from the wall, and so this angle has to become thicker, and it also has to both thicker and longer. And so in this case, we're talking about thermal bridging, and it's a very simple formula. It's the surface area multiplied by the mass. And so what we see here is that we've got a relatively large mass of steel Steel is the most thermally conductive material as a structural material that we would use. If you think about wood, wood is rather comparatively low mass, concrete less, moderate comparatively in the middle. But by far and large, steel is the most conductive and highest mass of material that we would use. So that's the first problem. And then secondly, the surface area. So commonly this angle would be face mounted to the structure, or in this case, the slab, and it would run along the complete perimeter of the building here. So if you could imagine, if it's a masonry building across 4 sides, this angle here at every floor junction is going to be creating a large thermal bridge. So the 3 problems that we'll address throughout the presentation and identify and how to solve those is first, the thermal bridging aspect. Again, as we see our insulation here, this angle has to get thicker to support this heavy veneer. So masonry is actually the heaviest veneer that we can use. So it has to support this load, and so that's why it gets thicker. It's the difficulty to install, which is always important when we're talking about costs. So these things are not just a material cost, but also how expensive it is for the mason to install this. And so we'll go ahead and get started. So this was an image that was created by RDH. They're located in Canada, one of the leading building envelope consultants for North America. And they wanted to put this image together to demonstrate the question, to answer the question of many people ask of, well, why are we doing this now? And this is really the kind of highlighting that answer. And so in previous years, we didn't have continuous insulation outbound. It was within the studs. And while this 4x4 by quarter inch angle, which is something important to remind yourselves of throughout the presentation, provides a bit of a thermal bridge, but there was significantly larger thermal bridges that were happening throughout this wall assembly here. So you think that we have studs that are 16 to 24 inches on center that are creating a thermal bridge. And so we transitioned and we said, okay, well, now it's a great idea to put continuous insulation outbound, but now we've created this larger angle. And so with 3 inches of insulation, this angle is easily going to be 4x7 by a ½ inch thick. So again, almost twice as long and twice as thick in this case. So we go from a 1/4 inch thick to a ½ inch thick. But what we want to get to is offsetting that angle. And rather than having a continuous thermal bridge, we want to go to a punctual connection. And so now our insulation is going through that connection and having limited connections that are transmitting the thermal bridging and going back to less mass. So again, we go from a 4x7 by ½ inch to a 4x4 by 1/4 inch angle here. And so this is what we're trying to achieve. But this is commonly what happens when we specify conventional angles. And so what you would want to see here is that here's your insulation plane, here's your masonry veneer, and then you have your CMU block or your backup wall and your floor that you'd be walking on. And so what you would want to see is this thermal anomaly happening within the insulation plane. And you can see this clearly happening well with the masonry time. You can also see this happening pretty well here with the through wall flashing that's going onto this angle. But as you can see, due to the mass and the surface area, we're getting a really large delta or anomaly that's happening well within the inside of the building. And so this is creating obviously energy loss due to the thermal conductivity, both in heating and cooling. And then the real tangible thing that you find is as you're walking closer to the outbounding walls of this building, your feet would be getting cold, especially in the winter months. But one thing to point out that many people don't understand because it's not tangible in the summer months is that the magnitude of heating energy loss in colder climates and cooling energy loss in warmer climates is within that same range. So regardless of how temperate or warm it is and we don't feel that cold, there is significant energy loss that's continuing out through the seasons. So that is a thermal model, but we want to also demonstrate some real world examples. And so what we see here is a thermal photo. And so this is an infrared photo that can identify where heat losses are happening or where something is not heated. So you can see this as a benchmark here at the top where this parapet wall is located and also at the windows. So as the image gets whiter, that means that there's more heating loss, whereas alternatively on the other side of the spectrum, when it gets closer to purples or blues, that means that there's no heat energy loss. And so what we can see here is this is an uninsulated stairwell condition. But so if you look here at the windows and here at the parapets, you can see how significant this angle here is located. So windows are, depending upon the schema of the building, could be limited. The parapet is only here at the top, but imagine all the energy loss that's continually happening at every floor level in this location. And so these are the things that we really want to make sure that we pay attention to, because this is the easiest path to make sure that our buildings are high performing here. So there are other things that are within this assembly, such as masonry ties. But again, masonry ties are, even though they're jumbled together, 16 by 24 inches on center, the mass is relatively low. And so this is why we're not seeing that gradient loss in the insulation areas within this wall assembly. So I think this is one of the bigger points that is really important, because we can always talk about the energy loss, but that's generally a disconnected conversation from the developer or the people that are building the building to the person that's owning the building. So the people that's generally building the building don't really care about energy loss. Their concern is on how can we build this the most efficiently, and recoup our investment for the construction cycle. And so this is really where those things are connected, because the lower the cost of the building transfers into the lower cost of this having to sell this unit for. And so this is some of the things that we're creating as a problem as we're increasing insulation and using conventional shelf angle. So if you're familiar with a lintel, a loose lintel, or older houses, a 4x4 by 1/4 inch angle would be commonly used, and that angle is 6 pounds per linear foot. But when we look into increasing our insulation thicknesses, we get to 4x7 by 3/8 or 4x7 by 1/2 inch, and you can see that this angle is now over double the weight. So from 60 and these angles are usually delivered on site at 10-foot sections. So we go from 60 pounds, which is a nice workout by a certain individual, but we get to 130 pounds, and that's surely going to require 2 people to lift. Then we get to 180 pounds. This is quite heavy and difficult to move around a job site, and then lift overhead and install. And then we've seen common details where the 8x8 by 1/2 inch or 8x8 by 1 inch is up to 510 pounds per 10-foot section. So if you can imagine that you're a mason and you're bidding a project and you're saying, oh man, this is 130 pounds, 180 pounds, 510 pounds. Well, I've got to put some pretty large labor numbers on this to install this. And this is where budgeting gets out of whack, and cheaper methods and materials are going to be used. So masonry is going to leave the wall in its ephes or it's some kind of inferior material to adjust for that budget. So additional increased costs that we have. So there's a cost of welding or drilling holes in the shelf angle. So these angles, they come flat, and then the holes have to be drilled, and then they have to be either welded to the structure or anchored into the structure. And then with cast in place slabs, you have to think that there's going to be rebar within the slab. And if this hole is not hit as they're drilling this hole, and this hole in the angle doesn't line up with now that they've hit a piece of rebar and they have to move over it, they have to continue to re-drill holes in the angle. Or if there's some kind of pre-installed anchor, that anchor doesn't line up with this hole, they're having to re-drill or reshift again. So that all the while they're lifting 180 pounds overhead, or they're having to have a machinery that's lifting this. Anchorage requirements are always going to be increasing depending upon the angle size. The size and weight of the shelf angle results in additional labor costs and equipment to hoist this angle. And then you have to think about the construction tolerances. It's very common that this concrete is not plumb and level. And so how do you get this angle to be straight and level to make sure that the masonry follows that same plumb and levelness? So these are all the coordination efforts that masons are having to include in their costs as they're installing angles like this. Also, these angles, when they're 4x7 by 1/2 inch, it's a flat plate. It's not something that's going to be commonly rolled steel. It's not going to be manufactured as you see it here on the screen. It's going to be a flat plate that has to be bent, then it has to be sent to a galvanizer to make sure that it doesn't corrode over a period of time. And then, so this is, I mean, lots of labor, lots of steps of coordination, even from the supply chain side, and we know the troubles there. And then lastly, lip brick. So we have to think that below this angle, there's a soft joint. Then you have this large angle, and then your masonry joint is 3/8 of an inch. And you wouldn't want to see this unsightly angle sticking out of your building. So what most architects would do is design lip bricks here to cheat or hide this angle. And from a brick that is a standard domestic brick would be in the dollar range. Lip bricks are going to be $3 to $5 per brick range, because you're either getting those from the plant that's producing them or they're cutting them on site, which creates a lot of waste. So as we transition into the presentation about the solutions that we offer for shelf angle design, one of the things that's always important to point out is what you should be expecting from a manufacturer that offers these solutions. So here at Faro, we've done extensive studying and analysis of our systems, both internally and externally through academia at the University of Alberta. So we own what you should expect is the manufacturer to provide you a fully delegated design submittal. And this should include everything from the types of anchors, the types of brackets, both in the depths and the heights, and the calculations that shows that it's supporting the loads and what it's being transferred back into the structure. And so you would want that, but you would also want to be able to make sure that all of that information has a credence. And so you can always come to ferocorp.com, FEORCORP.com, where you can download our tables and you can reference this quickly to make sure that the spacing and the types of brackets are to the standards. And so obviously you want to work with a manufacturer to say, hey, these are how these space to optimize cost, and have that reliance on the manufacturer to provide the specific design package. So this is our thermal bracket. So 3 years ago, and there was more and more professionals that were coming saying, hey, we really enjoy using fast brackets. Fast brackets were created in 1999, just to kind of show you how progressive Canada was. But more designers are saying, hey, we really need to find more thermal improvements for the fast bracket itself. And so there was two things that we wanted to make sure that we achieved. One, that we can obviously increase the thermal performance of the bracket. But in addition to that, we wanted to make sure that we didn't encroach on having to change any of the structural performance of the bracket, which is very important, again, because of all the testing that we've done. And so we looked at different things by aerogel coatings. It's a fluid applied coating that provides insulation. You may have heard about it used on the NASA spaceships. Using some kind of plastic shim behind it, but all of those things were creating structural problems, and the performance wasn't as we would have expected. And oddly enough, what came of it was actually just reducing the mass. So you hear me talking about this, and it's a very fundamental conversation, is just removing the mass of taking out any superfluous steel out of the bracket. As you can see here, as in this truss design, doing that improved it significantly, and at the same time, we did not have to reduce any of the structural capacity of the bracket. And so here's how the solution works. So here, and rather than this insulation being on the angle, now it's behind the angle, and we can achieve that by using our fast brackets. And so as you can see here, this is just a punctual location connection. They're going to be generally spaced 4 foot on center, but all of these things are going to be determined by our design team and our engineering team to optimize both the spacing and make sure that the brick can be supported adequately. So now our insulation's behind, and the brackets themselves are made as a standard out of 3/16 inch steel, and they're hot dip galvanized steel. We can make these out of stainless steel. That's always a possibility, but the cost is always the question of what's the purpose. So again, we're reducing the mass comparatively, and we're going to use a 4x4 by 1/4 inch angle here. And so we have our nice clean insulation plane and close to Nirvana as possible, where we can consider this continuous insulation, all the while still maintaining that space from the insulation and supporting the masonry outbound of that. So this the proprietary hole patterns, again, reduce the thermal conductivity, and these can be manufactured at any depths. So you'll see in the presentation, but we can make these up. We've made these up to 18 inches deep. So here's the thermal performance comparison So here's our benchmarks here. So we have 4 inches of mineral wool insulation, which is giving us a clear wall value of 16.8. And so we'll transition here to a conventional angle so that's going to reduce our R value or an effective R value to 10.8. And so this is where your thermal losses are happening at this angle, so you show comparatively. But using a fast bracket, again, offsetting the shelf angle here, reducing the mass, we get to an R value of 16.8, effective R value. And so you can see 16.8 to 16.7, sorry. And so this is an 83% comparative from 10.8 here, so an 83% improvement. And so as Andreas was saying, these are tenfold improvements that you're looking for Passive House, and we're the only manufacturer in North America that has a Passive House certified solution using offset shelf angle systems. Here's another study. This was unfortunately done just at the precipice of COVID, so many people may have not seen this study, but it was done by the Colorado Mason Redesign Guide. And I always like to focus on the second paragraph that they've written here. It says, for steel stud and concrete masonry backup wall structures, an additional 2 inches of exterior insulation or more may be needed to offset the thermal losses created with using a continuous shelf angle, as opposed to a standoff shelf angle. And so this study was done using our brackets. And so you can see that the thermal anomalies are tremendous in this 3-dimensional model. So here is one with the angle showing it structurally, and then you can see here how it's performing thermally, compared to how our punctual connection here with our 4x4 by quarter inch angle, how it's performing thermally here. And so, these things are important to point out, is that thermal losses are not just 2-dimensional. So it's not going to only impact the floor, but it also impacts the insulation here above and below at this connection. And you can see that demonstrated here clearly in these therm models. Here's a brief demonstration of an anecdotal what happens when you live in a cold climate such as Edmonton. So it's common for Edmonton to get to negative 40 degrees Celsius, which if you're into useless common knowledge, where those two paths cross for us imperial unit users, 40 degrees Celsius and 40 degrees Fahrenheit is at the same. So when you hear somebody say negative 40, it doesn't matter. It's just unbelievably cold. And so here's a little bit of a video on a cold winter day of what happens when you're using offset shelf angles compared to a fast bracket system. Yeah, thank you. So as we're moving on, so we want to talk about the simplified installation. Again, so this is really where the money matters when the construction costs go up, and those have to be transferred to the people that are buying the house or the unit there. So here's 3 common brackets that you would see as part of the designs that we provide for a building. So again, we're at Faro, we're always focused on what's the most optimized way of providing a solution. And so first, we're going to talk about our fast thermal bracket. This is our standard bracket. And what we would be supplying in this condition is just the bracket, the shim rod, the washer, and the shims here themselves. We don't necessarily require the angle to be bought from us. Again, we find that for carbon being as carbon friendly as possible, and also making sure that logistics costs don't increase, we don't require this angle to be bought from us. It can be provided locally. And so the anchors would be also supplied locally as desired. This is our inverted brackets. Again, where we'd be providing the brackets, the angle could be sourced locally. The only time that we're providing angle is when we punch the angle here for our lintel brackets, which would be used for over window conditions. So thermal brackets, you can find the adjustability both to make sure it's level and also when it's plumb. So if you could imagine the comparison when you're having a conventional angle anchored to the face of the slab, that angle is rigid. So if the slab is got a belly in it, or if it's pitching one side to the other, how do you make sure that that's plumb? Well, you're having to drill holes along the face of the slab to overcome that, and then it's not, you might get into some structural engineering issues. Whereas with fast brackets, you're going to anchor each one of these individually. This fast bracket, for instance, here is about 4 pounds. So you can imagine a contractor installing each one of these by hand. Each one is going to be installed individually to make sure that they're level. Once they're all level individually, and this at this slot here, you have an inch adjustability up and down. Once it's level, he would install the angle into this and it would be finished. We also see commonly where the slab is not plumb. So there's going to be needed shims for small deviations in the slab. For larger deviations, you would need to create a deeper bracket. And we manufacture these brackets starting at 2 inches, and then as the standard, we manufacture them at half-inch increments. So 2, 2.5, 3, 3.5, and up to at least 18 inches at this point in time. So as I mentioned, these can be made at any depth. So we commonly use this for details in New York, in the city, where there's an architectural condition where the piers, so in between the windows, the architect is having an architectural step out. So the slab is flat on the inside of the building, but the piers or the columns are stepping out. And so that's how that's achieved efficiently. Or alternatively, we can make these at any heights. And so if you could imagine in any high-rise building in New York, at some place, and especially hotels, for instance, where there's a mezzanine floor where they have banquet space, there's double height floors. So those are 20 feet high generally, rather comparatively to 10. And so brick would be coming down to a certain location, say 5 feet, which we've made these brackets as tall as 5 feet. And so you're going to be able to capture that condition without a lot of steel that would be very costly to create that detail. There are conditions that happen like this. I was just on a presentation with a large, well-known architecture firm in New York City just yesterday, and they, before I even showed this slide, they described it very well. So this is pretty common, where you go from 1 inch deep cavity here all the way to 6 inches of a deep cavity within 10 feet. And how would you do that alternatively with a conventional angle? It's very costly, unbelievably expensive to have multiple lengths of bent plate and stiffeners to try to achieve this as an alternative. So here's just another quick video as I take a sip of coffee to show how fast brackets would be installed in comparison with masonry ties. So the important detail here that you'll see is the through wall flashing, how this is achieved. There's different ways, and if you're looking for alternative ways for that to be installed, you can reach out to us and we can give you different options for that to be installed properly. So as we're going through, we'll point out some of the details. So again, we prefaced this earlier with our standard bracket. So this is the most common bracket that you would see on any given project. And so this would be used for all masonry to masonry conditions. So from one floor to the next where there's masonry, you would always see this bracket. Alternatively, depending upon the height of the brick and the depth of the insulation, we would also use these to span windows. So this is the most economical way, if it's possible, to use our system. And just to point out, again, there's a bit of a difference with the flashing detail. So instead of the flashing coming straight down and onto the angle as a more common detail, the insulation is going to come out over the insulation and then onto the angle and then to your drip edge flashing. So it still maintains that drainage plane to make sure that any water that's building up through wind-driven rain or moisture buildup in the cavity can exit properly. Next, we have our lintel bracket, and you can see here, this is now an extended lintel bracket. Standard brackets and lintel brackets can both be extended, but in this condition, which you can see here differently compared, is that the foot here in the standard bracket is supporting the horizontal foot of the angle, whereas now this toe, is supporting it in the vertical leg of the angle. And this is to make sure that you have a nice, clean, flat surface where the window would be in plane of the insulation. And so this is for energy efficiency performance. This is the ideal solution, is where your window is in plane with your window is in plane with the insulation here. I know in New York that's a bit different in some cases, but we have other solutions for shadow box windows. Then there's alternatives. So if you had dissimilar materials, or we also commonly use our inverted brackets when there's a terrace or some kind of, for instance, if there was a parapet wall here, and they wrapped the brick around it, or you had a terrace where there's insulation here and pavers, the bracket would be used because it's buried under the insulation. Or alternatively, if you were using a dissimilar material below, the one we're showing here is a fiber cement board, but you could use this quite easily with EIFS or any kind of manufactured stone, metal panel, etc. And so there are many alternatives on solving solutions that doesn't restrict the architectural design intent of the building. Then there are the cases when, again, the windows are much further down and the masonry needs to come down to match the elevation of the window condition here. And so in this case, when we have stud backup walls that are generally not stiff and the brackets that are longer than 25 inches, we would introduce our back brace plates. And so just for people that may not be familiar, a conventional design of this would have some kind of tube section or steel here. And then there would be a kicker that would come to the underside that would all be welded and anchored here to the underside. And so what you have is a situation where you're having to hide this kicker on the inside of the building, either by fur downs or drop down ceilings. Our solution solves that problem, whereas this brace is now going to be inside of the track of the studs. So it's nicely clean and hidden within the stud cavity wall. And so this gives you freedom to not have to design around these kickers here. And so this is a solution. In the event that you have a CMU backup wall or a stiff backup wall, for instance, you don't need the brace itself, and then it's sufficient here in this connection. Sometimes these brackets do get a little too long. So as I mentioned, sometimes brackets get as long as 5 feet, and you don't want to have flashing starting here at the top and coming all the way down to 5 feet here on this area. It's not very costly, economical in that case. And so this is using at the advantage of our back brace plate here. And so this would be anchored into the slab. This would be initially anchored here to the back brace and then connected again here to the fax bracket that's going to be supporting the masonry. And so now, rather than having a long through-wall flashing, the through-wall flashing is only going to be over the fast bracket that's supporting the masonry. And this is a perfect design for long conditions, as I mentioned, with tall masonry walls that need to address this condition here. So another thing to point out, we commonly see, and so one thing to point out in New York City, I know this is for many people in Westchester, but you also have to consider about how your control joints are. And so here in this condition, if you had an opening, you would have a loose lintel over the garage door, for instance. And then you would, if it's a taller wall, you might have another area where you're supporting masonry above. And so you have an angle here, and then you have a loose lintel here. So you can imagine the cost that would be impacting of that. And then you're also having 2 control joints, which may be unsightly. If you are designing projects that are in New York City, also keep in mind any loose lintels that are wider than 4 feet would have to be fire coated, which is an intumescent paint, which is quite expensive. And so this is also an added expense. Whereas the solution that we would provide in this condition is we would anchor into the slab that's located here or the backup wall, and then we would bring all the angle down here to the overhead garage condition. So you only have 1 control joint here at this location. Again, this is saving costs and labor in these conditions here. So we do a lot of custom conditions. Designers and home developers don't want to be restricted by squares, and so there's always going to be design interest on how to achieve some of those things. And so as you can see here, this is where there's a brick that's stepping back within a pier. And so in this case, we make the custom angles to match that pier and also that brick that's stepping back here, as you can see. You also have corner conditions where we manufacture the custom angles to wrap around the curve, so it's curving around the face and then turning straight around the abounding building side. And then also, if you are trying to make an outstanding example of an aesthetic appeal, you rather than exposing the angle here below, you can have your brick coming down to the underside of that and being supported as well, to bring a more luxurious designing aesthetic. So as I mentioned earlier, in some cases, despite the recommendation and good design practices of having your windows in plane with your insulation, some designers want to push that window back for this shadow box effect here. And so in that case, if you didn't have a solution there and you're designing with fast brackets, if you were looking from outside the window, you would see the insulation exposed. And obviously that's not something that you would want to see. And so in that case, we provide our cavity concealer here. And this is a two-piece system in which you would install the track here in the back, install the bracket, your angle, the through-wall flashing, and quite at the end, right before you put your drip edge flashing on, you would put this over the angle, and then it would slip into this ribbon connection here, and that would give you a nice clean connection that you see in this rendering. This can come primed, or it can be painted in 37 different colors. We generally see it primed so it can be painted locally to make sure that it matches the window selection paint color. So for most of the presentation, you've seen that we are connecting to a cast in place slab, but there are other conditions that you would have to be connecting to. So there's steel stud backup systems. This one is one where the steel stud is stiffened by an extra plate here. And this is a good detail that can be done by the cold form stud manufacturer. The downside to this one is that you're restricted to the spacing of the studs, generally at 16 inches on center. Another alternative is to have a flat plate across the whole face of those studs, and then we can optimize the spacing based upon the bracket's load conditions there. If you had a spandrel beam or some kind of condition where you're building a steel structure, this is our condition for W sections. So we would provide a small, a 4x4 by 1/4 inch angle that would be anchored to the flange of the W section. Then the bracket would be connected, and then you would have your masonry support angle here. For tube sections, in this case, we would either have two options. You would either drill through the tube section and anchor to the backside, or use a proprietary steel expansion anchor like a Lindafter bolt. And then for thin slabs, be it a composite deck or a hollow core deck, where the face of the concrete is not deep enough, then we would anchor to the top. And so in this case, we have here a steel studs over a corrugated metal deck system or composite deck. And so we would anchor it, we would provide a connection here into the track. And then again, similar to the steel connection, we would have that connected to the bracket and then your masonry support angle here. For CMU conditions, it's very simple. You either drill in with an expansion anchor or an epoxy coated anchor, or you can also through bolt it. For slabs, there's an expansion anchor option, anchor channels, or embeds or wedge inserts that are commonly referred to. And so there's many connections that we can provide based upon the structure or the backup connections that we're going to be transferring our loads into. Some other custom details. So here's our double bracket. So we use this commonly for corbelled conditions where the brick is stepping out for another architectural reveal. This is our fast flex system. So rather than having square boring corners, we can also make radiuses here. And if you've ever tried to do this with conventional angle, it's nearly impossible to get somebody to roll steel to match the curvature of a slab. So in this case, we cut the angle in segmented areas and we provide a tool for it to be bent. And this is being pinned back by our fast brackets here. As you've seen earlier with custom angle supports here, we provide these to match the profile of the piers or the custom conditions, and then our concealed lintel clips for more aesthetic appeal. So this is the time of the presentation where you may have sat in some and you're like, wow, I've really enjoyed this product. I think I can use it, but I'm interested, how much is this going to cost? So you're the brave soul that's asked that question. And the presentation, unfortunately, the presenter usually starts with things such as return on investment or life cycle costs. And in many cases, that's not the first position you would want to be in, especially when you have to balance the cost of things. And so I'm really proud at Faro. Our solutions are going to be not only cheaper in materials, but also in labor. And I'd like to take you through that. So as part of the presentation, we've talked about 4 inches of brick, inch air cavity, 4 inches of insulation, which would require you a 4x7 by ½ inch angle here, which provide us a assembly R value of 10.8. And that angle is going to be at minimum $21.25, 25 cents per linear foot. Now, if we compare that to our fast bracket assembly, again, same standards here, and we're going to have a R value of 16.7. And so the brackets here are $24 in this condition, $24 per bracket with a 4-foot spacing. It gives us a $6 per linear foot cost. And we're going to use a 4x4 by quarter inch angle here, which is $7.25. And that gives us a $13.25 assembly cost. So we're at $7 to $8 per linear foot of savings here. And this, again, this is just talking about the materials here. This is not talking about drilling these holes or any installation costs. So then you might have conditions where you're having to drop it down, as we've talked about throughout the presentation. And so this is a common detail for that. And so here we have a tube section or HSS plate, a knife plate here to span the insulation, 4x4 by 5/6 inch angle, and then Nelson studs here, along with the slab angle here that is being used as the pour stop. And this is a $95 per linear foot cost. And then we have, and this is all going to be done by a steel erector. So this is going to have to be welded. It's going to, you're adding an additional trade. At Faro, we always advocate for a mason to install our system because now you're reducing a labor trade, and the mason is generally more concerned about this being plumb and level than the steel erector. It's just the people who are installing these bricks are really focused on making sure that this is going to be plumb and level, whereas the steel fabricator, once he installs the steel, that's kind of where his scope ends. And so here we have our extended lintel brackets that are going to be anchored again rather than welded. So at 4-foot spacing with a punch shelf angle here, 4x4 by quarter inch, and we're at $32 per linear foot. And that's a $63 per linear foot savings. So as the conditions become more obtuse and harder to install, require more steel, again, it goes back to the mass of materials, and so the cost savings further increase. And so now we talk about some of the additional savings that we go into labor. We have more and more masons coming to us now after their first experience using fast brackets and saying, hey, we're now on just going to use this because this is our value engineered option. So when they're seeing conventional angles specified, they're actually switching to a fast bracket system now at this point. And it's for these reasons. They don't have to worry about the labor for hoisting or installing large angles. They can also recommend to the design team that there's no longer these lip bricks that are necessary that are having to be cut on site. I'm not sure if anybody's familiar what you look like when you're cutting a clay masonry brick on site. It looks like you've been in a butcher shop for quite a bit of time because you're using a wet saw and the clay masonry dust is flying back on you and you look completely bloody. So if you can imagine that. And so lower cost of shelf angles, so the span of the cavity, so smaller size shelf angles can be used. So less freight cost to the job site, and that angle can be sourced locally, and it can be sourced more readily available as well compared to a larger angle. Again, no welding or drilling into the shelf angle, as the bracket already has its hole in it, and you're installing an angle that is coming directly to site and going to be rolled into that bracket itself. Just as we're wrapping up, we'll talk about some quick comparisons. So there are solutions out there alternatively. We just always want to point out the key differences. So there's ones that were we ad hoc solutions. And so this is a tube section here welded to an angle, and this is another angle welded to the angle that's supporting the masonry. The biggest thing to keep in mind is that the structural engineer is going to have to own this, whereas a manufacturer such as ourselves is going to own this design. The engineer of record is going to have to own this, which is generally not within their interest. This is also quite expensive, labor intensive, no adjustability as we have built into the fast bracket here, and surely inferior thermal performance. This was something that used to be available, but no longer available in North America, which is a manufactured knife plate solution. And the problem with this is that you were having to buy this knife plate that's welded to the angle and this anchor channel, and that was sourced far, far away from Westchester, New York. And you're having to buy this all as an assembly system. Whereas with our fast brackets, you were only having to, for most conditions, having to buy our standard bracket here, and the angle would be sourced locally. And we don't require any specific anchors. We don't require you to buy the anchors from us. We're going to design with what's most efficient to design with, and what's more the preference of the installer. Some people have gotten enamored with these plastic pads, and there's a fallacy that most people don't understand of what's the problem with using pad material. First, it's not really a thermal break, as people would like to say it, because you have to start calculating these things. So while there's a non-composite material, which is not thermally conductive, you still have to specify a large angle here, which does create a thermal conductivity that you have to account for. Also, because of the low density of this material, you have to increase the amount of bolts that are on this that are inserted into this angle here to support the creep and deflection that could possibly happen with this plastic material. And you're really not achieving. So your costs are increasing again. So this angle still has to support the thickness of the insulation that's on it, and it has the air cavity here. So, and then you have to think non-composite materials really are not good for fire conditions. And so you have to consider, how do you fireproof this properly as well. And so we just want to also point out both the cost and the thermal performance with considering using pads. So 4-foot spacing, again, we kind of went over this. 4-foot spacing, $7.25. Now we're including the bolt at 4 foot on center, which gives us an assembly cost of $16.50. The composite pad, same price on per linear foot as the bracket, but then you can see where the prices start to really increase, because we're going to have to make sure that that angle is going to span the insulation area, and so that's $21 a linear foot. And then your anchors are going to have to be reduced. You're going to have to go to 2 foot on center, which gives you a assembled value of $30.38. So it's double in this case. And we've had people ask, well, what if I was to add the pad behind the bracket? And my simple answer is there's not much more juice to squeeze out of that, especially for the cost that we're seeing here, adding an additional $6 per linear foot. So I'll take you through. So we have our base using conventional shelf angle. That's an effective R value of 10.8. Then we have our conventional angle with a thermal pad, our plastic pad, and that gets us an effective R value of 12.4, which is a good improvement of 30% compared to the base. Using a fast bracket, you get to 16.7, which is pretty close to the clear wall value, and that's an 83% improvement from the base. And then we say, okay, well, how about that fast bracket with the plastic pad here? And that gets us an R value of 17, for the assembly value. But we're 0.3 improvement, or a 3% improvement from the fast bracket. And I wonder if many people would say, well, an additional $6 per linear foot is really worth a 3% improvement, or a 0.3 increase of R value. I really don't see it, but there could be conditions where that might be interesting. So we have done over 1,800 projects in North America. It's close to 50-50 Canadian and United States. And the United States is growing ever more every day, just by the sheer amount of construction that happens in the United States. And you can use it in anything. And so from single family homes, which we've done, you can also use it dimensional lumber, CLT, all the common construction materials that you generally see on the job site, from museums to stadiums to academia and multifamily housing. There's really no limitations on when you would use fast brackets. It's just a matter of, hey, do you have a really large angle, and can you use an alternative like fast brackets to reduce the cost and improve the thermal efficiency? As Andreas, as the leader for the New York Passive House, and we are as well. We've done the 4 passive house multifamily structures in New York City that has masonry, that has used fast brackets. Some of the examples that you might, if you're in the city, you could see, and we do roughly 20 projects every month with fast brackets. And that's kind of the average where it goes right now, from starting to ones are under completion. Again, and we're the only North American manufacturer that can say that we have a certified component for passive house conditions. And so if you are interested in that, we can help you with the assembly. Not only do we provide structural submittals, we can also provide thermal submittals. It is an added cost, but if you're looking to achieve certain performance requirements, we can provide a specific thermal model for that given connection on your building. So it's not a standard thermal model, it's actually specific to that building, and we can provide that. So that's the end of our presentation for today. We'll stop here, and so I will pass it back to Michael.
Actually, we'll pass it back to Ron.
Oh, Ron, sorry.
No worries. So great. Thank you for the excellent presentation. We have a few questions, if we would. So one, is the system patented unique to Faro? Is it just patented for Faro?
Yes, so this is a patented system that there's a significant amount of patents that are on it. It is a proprietary and patented system that we continue to innovate and patent as we go through designs. Yes.
Great. How long has the product been in use?
Since 1999.
Excellent. What's the life expectancy with the stainless steel versus the corrugated?
Generally, I would say it's the same. The times where you would think about using stainless,
Galvanized, I mean, sorry about that. Sorry.
Yeah, sorry. Yeah, for sure. Yeah, so there's hot dip galvanized, and that's a chemical process where there's molten zinc that you're dipping carbon steel into, and there's a chemical reaction that's actually happening where the molten zinc is adhering and infusing a new chemical into that carbon steel. So it's a very robust system. It's not something that you would see like where you would scratch it off and then you would have exposed carbon steel. I don't know exactly the life expectancy of hot dip galvanized compared to stainless, but the times when you're looking into a stainless alternate is either a really long life cycles. So this is when you think about academia projects, or alternatively, if there's a chloride condition. And so you think about those chloride conditions are usually along areas where there's a significant amount of salt spray that's coming from the oceans, or if it's in conditions where there's chlorides in the air, such as pools or aquatic sensors, for instance. So those are the times when you really start to consider using stainless as compared to hot dip galvanized.
Okay. Is there a system for shelf angle replacement over existing windows and masonry walls for older brick buildings?
Yeah, you can definitely do that. We have done that in restoration, because that does happen for sure. You can imagine that in prior construction of buildings, the angles were not hot dip galvanized, and they might have been just primed and not even spray galvanized, and they've started to rust out, or there wasn't a good detail of making sure that water was leaving the building. And so those angles have started to corrode, and it's created issues. And so as part of restoration, you're having to take back brick and reinstall it. And so that is definitely a possibility for restoration work, where you're taking off brick and reinstalling new angles there. Absolutely.
Excellent. Does a Faro system work with modular construction, and do you communicate with the modular supplier to finalize the plans?
We haven't entered into that arena, but as far as modular construction, that being said, that's not something that would be a problem. I could foresee that happening quite easily. There are people that are looking into modular masonry walls, where they actually bring out the walls similar to precast, and we've created solutions for that. As far as full modular buildings, I think you just have to make sure that you keep care of delivery of the masonry walls that are adhered to it. So that also comes in part of with the masonry ties as well. So those are all coordination things that can be achieved.
Excellent. Does the system work in high earthquake areas?
Yeah, so with fast brackets, and you keep in mind with fast brackets, those are supporting gravity loads, and so with angle or with even conventional angles, that's going to be supporting gravity loads. The way that you address a earthquake conditions or racking that you would consider or of the building is through your masonry ties. And so your masonry ties, in that case, with earthquake conditions, you're having a wire from your masonry tie, and then there's going to be an extended wire that's going to be within the brick, and that's how you address high seismic conditions. So the fast bracket can be used in seismic conditions, but the way that you address seismic activity is through your masonry ties and the wire that would be in the brick veneer itself.
Okay. Who inspects all this to make sure that it's performed correctly? Do you guys do that? Do you offer installation training? How does that work?
We do provide installation training, and so there is a level of obviously making sure as through the coordination process. So there's steps throughout the process, right? So generally, architects that are familiar with us, they have our CAD details where they're installing it, they're inserting it into their CAD drawings. Ones that are not familiar, we take them through a design consult process where we're showing them how they should detail it properly, or alternatively, they're sending us the CAD drawings and we're inserting our CAD drawings over that where they can toggle those on and off as layers. And then once it gets to the general contractor when they're bidding it, or to the mason when they're bidding it, we're talking about the proper means and methods of installation.
So I guess that means that you do provide technical assistance, including plan reviews and suggestions?
Absolutely, and we're providing shop drawings or submittals that are signed and sealed with a New York, in this case, a New York State license, or any other state that you might be those designs are being constructed in.
Great. And let's see. A lot of fantastic responses, by the way. People love this product. Can you tell us what you were doing with the videos? Just review real quickly because the sound didn't come through on either one of those, unfortunately. So.
Oh yeah, that's right. My apologies. There's a small little radio button that you have to click before the presentation, which I failed to do. Yeah, so the first one is really just showing you kind of an anecdotal display of how much of an impact of a conventional angle is reducing the thermal efficiency of that. So that's the first one with the ice block display. And then the second one's really just showing about coordination with your masonry ties and the fast brackets, and then how your through-wall flashing would be installed there.
Outstanding. Can you speak a little bit about some of your other Ferrell products, including the Corax rain screen panel?
Yeah, so Corax rain screen. So if you're familiar with EFIS, there's a problem with EFIS that's, and I don't want to get on a soapbox here, but there's a problem with EFIS is that if you don't make sure that the moisture is not exiting the cavity properly, you start to create that moisture gets trapped. So if you could imagine, you have your dense glass or your sheathing, you have your EFIS or your insulation. That's where the render is going to be installed on the outside. And if you don't have proper insulation exiting strategies, that moisture gets trapped, and that moisture generally starts to vapor drive into the building because foam insulations don't have they have very little vapor permeability. And so that vapor drive happens into the building, and this is when studs get wet. This is when cold form studs start to rust. And there's been clear examples of what happens when that happens, when you have vapor drive into the building. In Vancouver, Canada, there was the Olympic buildings in Whistler. After the Olympics, the Winter Olympics there, after a period of years, they were having mold issues, and they started to pull the building back. And they could actually take the studs and squeeze them with their hands and crush them. There's many buildings in Florida where it's quite humid, as much as it is like here in New Orleans. Where you have very similar conditions, or even with cold form studs, that vapor drive starts to rust out the tracks of the cold form studs. And so Corax, that was a long answer to the problem. The solution is with Corax, you're creating the drainage plane within the insulation. So you can put your render over the face of the insulation, and you have a clear drainage plane between it. Or alternatively, if you're installing any kind of other materials such as fiber cement boards, you can install it and you have still maintaining that clear drainage plan there.
Excellent. And if people want to get a hold of you, what's the best way?
Yeah, so there's a couple different ways where depending on what you're trying to learn or ask for us. So you can always find information about our company at ferrocorp.com. That's F as in Frank, E as in Echo, R as in Robert, O as in Oscar, CORP.com. You can also reach out to me. My email address is akimble, KIMBLE, at ferrocorp.com. And if you're looking for project updates or information that we're sharing on different products or projects that we're working on, you can always find us on LinkedIn and our LinkedIn profile at FerroCorp as well.
Outstanding. Any last words you'd like to share with everyone?
No, thank you so much for your time. I appreciate the audience. And if there's anything that we can help you out with your further designs or constructions, please reach out to us. We look forward to working with you. Thank you all.
And
thank you, Ron. I appreciate that. Adam, people want your contact information. You'll be sending certificates to everybody that's on the call besides posting or posting their AA credits. And when you do send the certificates, obviously you're going to send them your contact information as well. So
yep, and I just put my email address in the chat box as well for anybody just as a quick copy paste.
Thank you, Adam Kimball. Appreciate it. Thank you, Andreas Benzing and John Opperman for a great bonus presentation. Ron Kamen, always great to have to be on the Earth Kind Energy ubiquitous web platform. Bonnie, thank you. And Westchester Magazine, we thank you for being our sponsor. And remember, October 13th, we're going live at Westchester Magazine with Certainteed. There will be food, there will be adult beverages, just like the old days. We're going to go live every other presentation, Zoom in between. So thank you all for being on the presentation, and we'll see you next month.
Thank you, guys. Take care. Bye-bye.
Thanks all. Take care, everyone. Thank you, Mr. Murphy, for your wonderful presentations as always. Take care, everybody. See you next month.